watching Darasa Online.
Welcome again, students on Darasa Online. Today we are going to study physics and our topic is mechanics. We are going to look at a very small part of a subtopic of a circular motion to a section which is dealing with the motion of a body in a vertical circle. I'm Cyprian Mgina.
You are watching Darasa Online.
So, with this lesson, whenever we talk about a motion of a body in a vertical circle, this is a pure circular motion, just like when we are looking at a body which is rotating in a normal horizontal circle. With a motion of a body in a circle, vertical circle, there are such kind of variations of which we are just going to look briefly, of which I know you have already learned about this. And with this kind of a motion, there are so many applications with such a vertical motion of a body, circular motion of a body. There are so many applications in our daily life. For example, you might be able to find somebody moving a bucket of water in a circle without the water falling it down, or into some particular games. Some games can just be driven in a particular cycle to a certain particular speed without making those childs or who are just riding such kind of trains moving in a circle be able to fall down. And there are so many applications as we shall just be able to see later. But actually, what you are just going to talk about this, that there are forces which are really keeping this particular body to move comfortably in such a circular motion, a vertical circular motion. So we are going to have a basic sketch of such kind of a motion, and we are going to look those important formulas or situations which really takes a body in a vertical circle without any problem. Let's just assume that we are having such kind of a circle. If we are taking this to be a circle of a radius r, and the body is made to move in such a vertical circle with a certain radius, then there are, at any instant, this particular body could just be somewhere there. At any instant, that particular body could just be somewhere there. And we could just be able to see that if it's moving, let's say with a velocity v, there are forces which are really acting to this particular body which is moving such a vertical circle. There is first of all, there is if this body is of a mass m, there is a weight mg which is acting vertically downward, and also there is a tension T which is keeping on holding this particular body to move in a circle. But if we are going to resolve these forces, we could be able to resolve along the circular path, and this gives us an mg sine theta. If I'm taking this angle inclined to the vertical is theta, and if we're going to take along the string, then this will just be equal to mg cos theta, because this angle from geometry will just be the same as this angle if I'm taking this to be the direction of the weight which is acting perpendicularly downward. So this particular body can just be moving in a circle. But the very important points are the points whenever a body have reached at the top there, and whenever have reached at the bottom there. And sometimes we could be able to consider whenever a body have reached at that particular point, just on the horizontal line. That is, whenever a string is in the horizontal line. So all in all, whenever a body is moving in a circle, there is a centripetal force which is really maintains this particular body to move in a circle, the centripetal force. So we can just try to look those important points at the top and at the bottom. Let us start to look at the top. That at the top, the body can be moving, let's say, with the velocity VA. And at the bottom, this particular body can be moving horizontally with the velocity, call it VB. So let's just look whenever it is at the top. Whenever it is at the top, the weight for the body is acting downward there, which is just equal to mg. If I'm taking this particular body, is of a mass m. And again, the tension force is also acting downward. So I can take this to be the tension at that particular, at the moment the body is at the highest point, such that the actual centripetal force which maintains this body to move in such a particular circle, we'll just be able to find that it's just equal to mg plus that particular tension. So we're having the mg plus that particular tension. This is the necessary force which is really keeping this particular body to move in a circle. So this will just be equal to mv, call this v at a over r. So this will just be our expression, such that if I needed to determine the tension at a point A, we'll just be having mv squared at a over r minus mg. And this is the tension which is obtained at the highest point there. This is the tension which is obtained at the highest point there. And we can be able to find the tension at a point B, that is at the lowest point. The tension at the lowest point, we'll just be able to find that whenever a body is moving here, there will be a weight which is acting vertically downward, and that is mg. But there is a tension force which is acting upward. Let me call this to be equal to T sub B. The necessary force to make this particular body move in a circle, the centripetal force, will just be equal to the difference of the two forces. That is the tension at a point B minus the weight. This provides the necessary centripetal force which is really making this particular body move in a circle. And therefore, we could be able to find that the tension at a point B at the lowest point, this will just be equal to mvb squared over r minus plus, not mg, minus plus mg. So we are having this to be the second expression. Now, if we are comparing these two particular expressions, taking a body to be moving, let's say, in the same radius, you'll just be able to find that the tension that is developed at the lowest point is maximum. So the body, whenever it's moving in a vertical circle, the body the tension which is developed in the string at the lowest point provides the maximum tension, which is TB, and the minimum tension is obtained whenever the body is passing at the top point, that is at point A. Because remember that the acceleration due to gravity is always acting to the negative y direction. And therefore, we are having this and we are taking this as the minimum tension, and this as the maximum tension. Okay, so having obtained the maximum tension which is into the string, which is obtained whenever a body passes at the lowest point, and the minimum tension whenever a body is passing at the highest point in such a vertical circle, then you could just be able, and the G is acting vertically downward, then you could just be able to understand for sure that this kind of a circular motion is not uniform. Why? Because as the body is moving upward, then it's just the gravitational force opposes its motion. And whenever a body is moving downwards, let's say from point A to point B, the gravitational force supports the motion. And therefore, you'll just be able to find that there is such kind of a variation of a motion. And therefore, the motion of a body in a vertical circle is not uniform. And this, for that particular case, that situation could help us to understand what kind of a velocity obtained whenever a body is passing at the highest point there, and what kind of a velocity of a body obtained whenever a body is passing at the lowest point there. So we could just be able to determine what is the VA and what is the VB. And all of this can just be derived together with some other things or some other values which can just be asked, and we will just be able to look this to some particular areas of questions which are more challenging to you. We'll just be able to do some very simple derivations so as you can be able to understand an expression for the velocity whenever a body is passing at the top and whenever it's passing at the bottom, or whenever it's passing at point C, moving vertically upward. At that particular point C, whenever a body is moving vertically upward. That is the velocity at a point C. Just the same as the velocity whenever a body is moving vertically downward at this particular point, if I call this particular point D. So we'll just be able to look at this whenever we'll just be solving some basic questions which are really more challenging to you.
You are watching Darasa Online.
Okay, let us just look and see those questions I'm having, and I hope it will help you to go with me through those particular challenging areas. Okay, our first question is this one. It says that a pilot of 70 kilogram mass in a jet aircraft is executing loop a circle with a constant speed of 380 kilometers per hour. If the radius of a circular loop is 250 meters, now determine the force exerted by a seat on a pilot at the top and at the bottom of the loop. This is a question which takes us to what I have already mentioned, that we are having a pilot of that particular mass, 70 kilogram, is in his jet aircraft. Now is executing a loop with a constant speed, executing a loop of a circle with a constant speed. This is a vertical circle, okay, with a constant speed. Now, if the radius of a circular loop is 250 meters, now we need to determine the force exerted by a seat on a pilot at the top and at the bottom of the loop. So we go back to our question here again, that we are having such kind of a plane moving in the way we have already mentioned previously. So we are having a plane like that, which is moving in such a vertical circle. It's looping a loop. Now, we are looking at the moment, the plane is at the top there, and at the moment, the plane is down there. And therefore, if we are taking this to be the circular loop, with the radius r there, which is 250 meters, the radius r there is 250 meters, and the mass of the pilot is 70 kilogram. And we are taking the speed at which this particular plane is looping a circle. V is 380 kilometers per hour. So we need to calculate now. We need to calculate the force exerted by a seat on a pilot. This is the reaction force that particular pilot will be feeling whenever he is looping a loop, moving around a circle, looping a circle. It means that if we are taking this to be the pilot seat, so it means that his weight will be acting downward there, which is the mg. Now the reaction force is acting upward there. So that is the thing which we are just going to look. The reaction he is going to feel from his feet, from his seat, whenever his plane is looping a loop in that particular radius with that particular speed. So our first case is to convert this velocity 380 kilometers per hour to go into a meters per second. So the 380 kilometers per hour, this is just like 380 times 1,000. We convert into meters and we divide per second, then we divide by 60 times 60, because 1 hour have got 3,600 seconds. So if you compute it over there, you are just going to get an answer so quickly by using your calculator. That is 380. That is 380 times 1,000. Then we divide by 3,600. This is 105.55. 105.5. Let me take 56 meters per second. And then we are asked to determine the force exerted by a seat on a pilot at the top and at the bottom. So let us start at the top. At the top, we all know that the weight of this particular pilot is equal to mg, is acting downward, but the reaction force, remember, it's looping a loop, so it'll just be like his head pointing downward. So the reaction force will also be pointing to the same direction. Okay, so that we'll just be able now to find that the force which is necessary to provide it, or to make him be able to move in or to loop comfortably in that particular circle will just correspond with this particular expression we have just found previously, such that instead of now a tension T in the string, now we are having a reaction R. So we'll just be able to find that the reaction R plus mg, this will just be equal to the necessary centripetal force, which is keeping this particular pilot to loop a loop. So that the reaction R now, this will just be equal to mv squared over R minus mg. And if you compute here, you'll just be able to find that the mass of this pilot is 70 kilogram, and the velocity we have already changed over there, which is 105.56. So we square this over radius r. So we take this minus mg, and the radius there is given, which is the loop have a radius of 250. So instead of putting r here, this is 250 meters. So we could just be able to compute and be able to take the difference. And the mg there is the mass, is the weight of a person, which is 70 times 9.8. So that we could just be able to compute here comfortably that if I'm taking 105, So this will be equal to 3119.74 minus mg. The mass is 70 and the g is 9.8. So we'll be having 3119.74 minus, here is 600, this is 686. So if you take the difference here, then we are just going to get we're just going to get 2,433.74 newtons. So the reaction of this particular pilot is going to feel whenever it's looping the loop at the top will be equal to this much. Will be equal to this much. This is the bigger force. But let us go and look the second reaction, or what we call the force is going to be exerted on his feet, on his seat, on a pilot whenever he is at the lowest point, that is at the bottom of the loop. So at the bottom of the loop, we are now just going to use this kind of an equation number 2. And we can just be able to solve this. That whenever is here now, his weight is mg acting downward, but the reaction from his feet is acting upward there. So this is around, let me call this to be R2. This is R1 at the top. So that we could be able to see that the necessary force to make him loop a loop comfortably, we are taking the difference, the necessary centripetal force will just be equal to the difference of the two forces, as we can be able to see from this particular expression. That is R2 minus mg, this is equal to mv squared over r. But all other values are being given so that we could be able to determine now the reaction R on his seat. So this will just be equal to mv squared over r plus mg. So if we substitute it there, then we are just going to have we could be able to simplify mv squared over r plus mg. We are just going to use the same values over there, whereby mv squared over r, it is this much, which is equal to this much, but instead of minus now we are adding, so that we are going to have this much now plus that much, that we are just going to have, 3119.74 for this value, plus mg, which is 686. And if you add there, you are just going to get we're just going to get 3,805. 3,805.74. So this is the reaction a pilot will feel whenever his plane is flying at the lowest point of that particular loop, a circular loop, with the condition which is given in that particular question. Okay, students, let us now go to the second example, which is also more or less challenging to you. This question says that a bucket is filled with water. A bucket filled with water is having a mass of 8 kilograms and attached to the lower end of the string 1.5 meters long. If it is rotated about the vertical circle such that it passes at the highest point with a velocity of 3.575 meters per second, will the string become slack or remain tight at the highest point? Justify your answer. That is A. B. Based on the answer in part A, will the water spill out of the bucket or not? Give reasons. C. What will be the minimum speed when this bucket passes at the lowest point? So students, this is the question. We are having a bucket which is moved in a vertical circle, and this bucket is filled with water. Its total mass with the water is 8 kilograms. And the string at which is made to be moved in a vertical circle have a length of 1.5 meters. And it is rotated with that particular velocity, 3.75 meters per second. So you can answer one question after another. Let us have a simple sketch of such a bucket moved in such a vertical circle. So we are having a string holding such a bucket passing at the lowest point. Let me take this to be point A, the highest point, and point B, the lowest point. So at the moment it's passing at the highest point, will look like that. So that is point O, is the center. And we are having the length of the string. The length of the string is 1.5 meters. So we could just be able to see if actually the string will become slack or remain tight at the highest point or not. So to determine if the string will slack whenever that bucket passes at the highest point, we need now just to determine what will just be the minimum velocity. What will just be the minimum velocity of a bucket whenever it passes at the top there? Let me call this to be equal to VA. And the maximum velocity whenever a body is passing at the bottom, which is VB. So all in all, it will take us to those forces we have just solved previously, where we have said that whenever a body is at the top, its weight mg is acting downward together with the tension T, which is also acting downward, such that for looping a loop be successful, the necessary force to provide the centripetal force will be equal to T plus mg, which is equal to mv. That is the tension T at the top plus mg. This is just equal to mv squared over r. But remember that if we are taking T to be the tension into the string at the top, for the minimum velocity, which will just make the whole exercise of moving around the circle successful, the minimum tension there, T, should be equal to 0. So we put T there to be equal to a 0, and therefore we'll just be able to find that to our expression over there, we'll just be having that the mg will just be equal to mv squared over r. The mv squared over r. Such that if the mass is the same, then the minimum velocity v will just be equal to g times r. Or velocity v will just be equal to the square root of g times r. Now we need just to calculate this, to determine what will just be the minimum velocity whenever a bucket passes at the top. The G there is 9.8 and the radius is 1.5 meter. We just look for the square root of that particular expression.
You are watching Darasa Online.
So computing this using your calculator, you take 9.8 times 1.5, you get 100, you get 14.7. So if you look, the square root for that will be equal to 3.83. So this is the minimum velocity which can make the bucket be able to move at the top around such a circle comfortably without making the string holding a bucket slack. But here we are given that that particular bucket passes at the highest point with a velocity of 3.75. The velocity given there is 3.75. Now you need just to compare. Look with the velocity at which this bucket possesses whenever it's passing at the top, which is 3.75 meters per second, and the actual minimum velocity for such a bucket to possess without making a string slack. This velocity is smaller than that one. So it is for sure that if a bucket is moving at the top with this velocity, the string will be slack. So part A, the string will become slack. So for part A, the string will be slack. And all of these are the reasons of which mathematically justifies that the minimum velocity passing at the top is supposed to be 3.83 meters per second, but the actual velocity given is less than that, so it's for sure that the string will slack. So now we go to the second part. Based on the answer in part A, will the water spill out of the bucket or not? Give reasons. As we have already mentioned, that the necessary force to make the body move comfortably around a vertical circle and without making even the string slack, it is this one there, which can really be able to hold even the water and all of the things which are contained with that particular bucket and make the whole movement of the bucket, whenever it's passing at the top, remain with the same length and the string remain tight without having a slack. So if we are basing to the part A, the water will spill out because the velocity which the bucket is given there is really smaller than the actual minimum velocity at which that particular bucket is supposed to possess. Okay, we go to part C. What will be the minimum speed when this bucket passes at the lowest point? What will be the minimum speed when the bucket passes at the lowest point? To determine this minimum speed, whenever it's passing at the lowest point, to determine this particular minimum speed, which is the VB, it should be the velocity at whereby its total energy, whereby the total energy possessed by a body at the moment is passing at the bottom there. Whenever it reaches to the top there, due to the conservation of energy, should have a velocity which is just equal to V is equal to RG. Remember, the velocity at this particular point is just equal to R times G. So to determine this particular minimum velocity, we could just be able to look. The kind of the energy possessed by a body whenever it's passing at the bottom there. So that by the conservation of energy, the total kinetic energy possessed by a body at the bottom there should just be equal to the total energy which will just be possessed by the body whenever it is at the highest point there. So it goes like this. The total energy possessed at the bottom there is purely kinetic, which is just equal to a half times mass times velocity at b squared. So this will just be equal to the total energy possessed at the top. The total energy which is possessed at the top, which will just be equal to the total kinetic plus potential. The kinetic energy will just be equal to a half times mass times velocity at the top plus the potential energy, which is equal to mg times h. But remember, the height at the top is equal to twice of the radius. Remember, the height at the top is just equal to twice of the radius, because this radius plus this radius, that is equal to 2r. And the velocity VA at the top is just equal to the square root of rg. And the velocity at the top is just equal to the square root of rg. So we need just to substitute and be able to see what we're going to get. So here we are going to have a half times m times vb squared. This is just equal to a half times m. Now the VA, the square root of that is just equal to r times g plus mgh. So this is m times g, and h is just equal to 2r. And if we are going to divide by m throughout and multiply by 2, then we are just going to have the vb squared, the 2 goes and m goes. So I'm just going to remain with rg, and here the m goes, but the 2 will be there because we are multiplying by 2, so it will be equal to 2, and 2 times g 2 times g times 2r. And if written in a very good way, we're just going to have rg plus 4 rg, which is equal to 5 rg. So the velocity, the minimum velocity at a point B, you can be able to say that vb squared is just equal to the square root now of 5 times rg. So this is the minimum velocity at which the body is supposed to, the minimum velocity at which the body, minimum velocity of speed, whenever possessed by a bucket, whenever it is passing at the lowest point there, at this particular point. And we can now just be able to compute, because the radius of the vertical circle is given. That radius is the length of the string, which is 1.5 meters, and the g is known. So we can be able to compute this. That is 5 times 1.5 meters times 9.8. So we look for the square root of that particular expression. And using your calculator, you can just be able to compute this. That this is 5 times 1.5, the length of the string, times 9 times g, that is 9.8, which is 73.5. So if you look at the square root of that, you are getting 8.57. So this is the minimum velocity. This is the minimum velocity or minimum speed when this bucket passes at the lowest point. This is the minimum velocity whenever this particular bucket passes at the lowest point. Okay, students, these two questions are just a few which cannot be able to preempt all of the cases with regard to the motion in a vertical circle. I believe you might be having a lot of challenging questions, but we go for a break. When we come back, then I'll just be able to share. I'll be able to share with you one question. I'll give you that as a homework, and try to give you some hints of which you can be able to go about solving that particular question.
You are watching Darasa Online.
Okay, students. Here now we are having a question as a homework for you to do it at home. The question goes like this. A bucket full of water is rotated in a vertical circle of a radius 3.5 meters. A. Determine the period of revolution executed by this bucket such that the water will not fall out. B. Does the period obtained in part A maximum or minimum? Give reasons. You can be able to say that, you can be able to fail to start somewhere, but I could just be able to give you something which you need just to understand. If that is the bucket, which has just to be moved, let's say, in a vertical circle of that particular radius, R from the center, you need to determine the revolution executed to this bucket such that the water will not fall out. So the period of revolutions executed to this bucket such that the water will not fall out will depend upon the forces which can really be able to hold this particular water in a bucket. And very basically, you need just to look a situation whenever a bucket is passing at the top. Whenever a bucket is passing at the top. And you really need just to determine this. And also you need to determine whenever a bucket is also passing at the bottom there. So we are having the minimum velocity whenever it's passing at the top, as well as the minimum velocity whenever it's passing at the bottom. So to use this particular period, to use this particular minimum velocity whenever it's passing at the bottom, that particular velocity v, there's just be equal to the square root of 5 times g times r. So as long as this v is the minimum velocity, whenever a bucket is passing at the bottom, is the one which I'm just going to use than using the one at the top. Why? Because this is the minimum velocity at which this particular bucket will just be able to pass at the bottom. So upon using this, you know that v is just equal to r omega. So the omega, the angular velocity, this will just be equal to v over omega, that will just be equal to v over r. And if you proceed from there, you can eventually be able to obtain the value for the omega in radians per second. But you all know that the period t is just equal to 2 pi over omega. So from there, you can be able to determine, the period of revolutions, this period t. And this period, as long as you have just obtained by using the minimum velocity at which when a bucket is passing at the lowest point, this will be the maximum. This will be the maximum. So for a part B, the period obtained in part according to whatever obtained in part A, that particular period t will just be the maximum period. So I leave you, take this question at home and be able to compute for the angular velocity and finally obtain this particular period t, which is a maximum period for the reason I have already mentioned before. Thank you, students. I believe you will just be able to enjoy doing some more questions with regard to this particular part. But don't forget to do more revisions so that you won't be able to forget the way you can just be able to derive those basic formulas with regard to this particular motion of a body in a vertical circle, which really can take you to a very good understanding of solving any particular question with regard to the motion of a body in a vertical circle. So again, see you next time to our physics period.